Okay, so today we'll be talking about energy, work, and power in general. So what is meant by work or energy? When we're talking about work or energy, right? What do we mean by that? What do we mean by work and energy is basically how much يعني force is required to move something a specific distance. This is known as the working force or the energy consumed or provided or whatever for the object depending on each case. So for a simple example, let us say we have a block, all right, of a specific mass. We want to move it a distance of 30 meters, okay? And we are applying a force of, let's say, 5 newtons. All right, so we want the block to reach basically here. All right, so we're moving it 30 meters. If we apply a force of 5 newtons to find the work, it is simply the force times the distance it will cover. Okay, this is not the same as torque where you're multiplying by perpendicular distance. This is the distance moved. All right, so this is distance moved. So in this case, it would be a 5 Newton force times the 30-meter distance, which will give us 150, 150 Newton meter, also known as, in the case of energy, as joules. So this is 150 joules. So the SI unit for work is joules, all right? Which is basically the force times the moving distance. Okay, this is basically what it is for work in general, for any type of system, but work is also equal to energy. So this is the same thing. So when we're talking about work done or the energy, we mean the same exact concept. But when we're talking about energy, I'm pretty sure most of you have already been familiar with the two main types of energy that we usually look at, which is kinetic energy and potential energy. Okay, شو معناته هالشيئين؟ So kinetic energy is moving, you could say, left and right. بما معنى. It's not exactly that, but this is an easy way to remember it, as in if you have an object that is moving left and right. And potential energy is when something is moving up and down. معناته we have effect of gravity. All right, so when something is going up or going down, it is going to have a potential energy, either gaining it when going up or losing it when going down. So if it's going up, it is gaining potential energy. And if it's going down, it is losing potential energy. All right. In the case of kinetic energy, this depends on the velocity of the object. Okay. And the left and right depends on, mainly depends on, so basically when velocity is going up, and velocity is going up, you are gaining kinetic energy. And when velocity is going down, you are losing kinetic energy, right? And left and right just depends on the direction that you are assuming for where your positive and negative is, but that's not going to be too much of a big deal. The idea is as you are gaining more velocity, you're going to be having a higher kinetic energy. And if you're losing velocity, you are losing kinetic energy, it will become lower. So why is this dependent on the gravity and why is this dependent on velocity? We're going to look at that in a bit. But one last point I need to mention. So if our velocity is equal to 0, that means our kinetic energy is going to be equal to 0 because it is dependent on the velocity. And in this case, gravity is never going to be 0. However, it depends on the height of the object. So if the height of the object is equal to 0, and then remember, this is moving up and down. So if the height is at the ground or equal to 0, that means our potential energy is equal to 0. And we are going to look at both now in a bit. So for the first thing, kinetic energy. So how did we know that there's a relation with velocity? Very simple. Remember the very basic equation for energy or work. It is the force times the distance that is covered. All right. So let us say that we have an object that has a specific velocity, okay? So we know that, if you remember from linear equations, remember we have an equation which is v squared minus u squared is equal to 2as, where this is our final velocity, u is our initial velocity, and the a is the acceleration, and s is the distance that is covered, okay? Let's assume that it starts from rest, all right? So from rest, meaning u is equal to 0, okay? معناته هني we're gonna have v squared is equal to 2as. Let us rearrange this equation. Acceleration will be equal to v squared, we just divide 2s to the other side, 2s. Why am I finding the acceleration? Because remember, we need to find the force times the distance so we can find out what our work or our kinetic energy is. So in the case of kinetic energy, we're going to have an object. So this is for kinetic energy, all right? So we'll have an object that is moving from one point to another, and if it's at rest, there has to be an acceleration for it to have a velocity, because here we have u, which is equal 0, v final, or just v is a specific velocity, so that it will move, and you will have an applied force F, where F is equal to the mass of this object times acceleration. All right, that is why we need to find our acceleration. So acceleration is going to be in terms of the v squared to s, where s is our displacement, if you remember. All right, so s is basically our displacement from this point to this point, which is s. So our force is going to be equal to the mass. If we plug in this acceleration value for it, it's v squared over 2s. All right, and this is our force equation. What do we need to determine now? Our distance moved. We already have our distance moved, which is s. So we can say that our work, so this s is our distance moved, اللي هو displacement. So our work is going to be equal to what we know as our kinetic energy in this case, which is going to be the force times the distance s. In other words, kinetic energy is equal to the force, which is mv squared over 2s times s. And if you notice here, the s's will cancel. We will be left with our kinetic energy equation, which is kinetic energy is equal to mv squared over 2, or a more simpler way that you guys see this is half mv squared. All right, so this is our kinetic energy equation. Basically, this is how we can find the kinetic energy of an accelerating object. All right, as long as we have the mass and the velocity of the object. Remember that the mass is constant. Mass will never be 0, but velocity can be 0. This is why velocity is the determining value for your kinetic energy. Hence why I said earlier, as velocity is increasing, you're going to have a higher kinetic energy, and when it's decreasing, you're going to be losing, or even if it's 0, it's going to be 0 kinetic energy. Okay? So this is how we got this equation. You do not need to know all of this. All you need to know is you're going to be using this equation to find the kinetic energy of a moving object. Now, what about, this was for kinetic, what about potential energy? Potential energy. So as I said, potential energy is when an object is going up or down, right? So let's say we have an object that is going upwards or downwards, it doesn't matter, that is going upwards, let's say that for now, okay? So for potential energy, we're gonna have a specific height for this object. So let's say it's going upwards to this point, and this is the height that it's going to cover, h. All right, let's call this height h. Meaning that we need to move this block this distance h. So h is our moving distance. All right, so that the block will come here. Okay, so again, the same idea, but here we already have something known as our weight of the object, which is mg, which is weight, w. W is equal to mg. So in this case, now we need to overcome this mg. This force over here needs to overcome mg. So in other words, F has to also be equal to mg. Okay? So the force that we have has to be equal to, if we do our sigma Fy, obviously, then we're going to have F equals 0. That means F minus W is equal to 0 because F is upwards and mg is downwards, meaning F is equal to W. That's why we got F is equal to mg. Work done, or in this case, potential energy, is going to be equal to the force times the moving distance, which in this case is h. That's why we can say our potential energy equation is the force, which is mg h. Again, the derivation is not important. This equation is what is most important. Okay? Now, most of the time when you have an object, it's usually not just moving in one direction. It's not just going up and down. It is going at an angle, going up, left, right, whatever. So you're going to be having both kinetic energy and potential energy. So again, our kinetic energy equation is half mv squared, and our potential energy is mgh. Very simple. Very simple. These equations you need to know by heart because you will be using them in almost every energy question. Okay? So now let's talk about how these energies can be combined and how they work together. Let's look at an example, a very basic example where we have a ball on a slanted height. All right? Let's say we have a ball over here and it will fall and eventually reach the bottom over here at the ground. Okay? So this will be our distance that it is moving. Okay? Whatever distance it is. That's not what we want to focus on right now. What we want to focus on is these 2 points, these 2 phases this ball is in. فهني عندنا أول case, our first case, and then this is our second case when the ball is reaching the ground. So let's say the ball starts at rest. So in other words, let's say our initial velocity, or let's call it V1, is equal to 0. Yani someone is holding this ball before letting go. All right. So in our first state, our first stage, all right, we have V1 equals 0. And let us say that there is a height over here. Obviously, there has to be a height for this ball to move all the way down. Okay. So let's say that this height, let's call it h. Okay, let's call this height h. This is the height that we have, or we can call it also as h1. All right, so h1. So we have a specific height h1, whatever the value of it is. This is the height of the ball at point 1. Now let's look at point 2. Again, we're going to look at velocity and we're going to look at height. So here at point 2, our velocity, we have a velocity v2. It's not equal to 0 لأن it was accelerating due to gravity the ball until it went down. Once it reaches this point, it had a specific velocity. Nice. And now our height has all been gone. And we're at the ground level. So our h2 is equal to 0. Okay. So why am I talking about 2 specific points? How can we relate these 2 points together? So in mechanical dynamics, or in mechanics in general, we have something known as the conservation of energy. شو معناته the conservation of energy؟ معناته any energy cannot be created or destroyed. You guys should know this by now. يعني energy is never created or it is destroyed. It is always either transformed or transferred. يعني it is always changing from its type of energy to another type of energy. All right? So in this case, in phase 1, we had our kinetic energy 1 is equal to 0. But our potential energy 1 is not equal to 0. Why is kinetic energy equal to 0? Because our V1 is 0. And based on this equation, if you have a velocity of 0, your kinetic energy will be 0. The potential energy here is going to be equal to mass times gravity times our height h1. So we have a specific type of potential energy. Let's look at phase 2. In phase 2, our kinetic energy there is a value for it because we know we have a velocity. So it's going to be half mv2 squared. But our potential energy is equal to 0. Why? Because we no longer have any height over here. We are at the ground level. The conservation of energy says that our full energy that we have up here has to be equally available here in another state or transformed into another type. So in other words, what does this mean? معناته our state 1 energies should be equal to our state 2 energy. لأنه where else would it go? The energy had to be carried with this ball from this point to this point in some form or another. تمام? So if we look at it this way, معناته we have KE, our total energy at point 1 is KE1 plus PE1, which is our kinetic and potential energies, is equal to our KE2 plus our PE2. All right? We know that our kinetic energy 1 is 0, so this is just a 0 value. And we know that our potential energy 2 is equal to 0. معناته our potential energy 1 now, if we substitute for it, we have mgh1 is equal to the kinetic energy, which is half mv2 squared. If you notice from this equation, now we can also cancel the m's and find a direct relation between the velocity and the height, given one or the other. Yani if we have the height, we can find the velocity. If we have the velocity, we can find the height because g is a constant, which is the acceleration due to gravity. So if I want to write an equation in terms of h, so v will be equal to, stop using colors for now, so v is equal to, v2 squared at this point is equal to, if we take the 2 to the other side, it's 2gh1, or in other words, v squared or v2 is equal to the square root of 2gh1. Or you can just say velocity is equal to 2gh, just v and h in the case where it starts from rest and the final height is 0. Okay, but I want you guys to understand this concept very, very importantly. I need this of adding your potential and kinetic energies and equating them to each other. This is also known as our total work done. All right, so this is also equal to our total work done. How is it equal to that? So the total work done is equal to our energy from phase 1 minus our energy from phase 2. All right, yani the energy that we had at the beginning that we started with minus this energy. This isn't the total work done, this is the total work lost. All right, in this case there wasn't any work loss. Why? Because we have 1 is equal to 2 in the conservation of energy. But in some cases we might have a frictional force in the system, or we might have heat loss, but in your case you're only going to see frictional force in the system. This will generate a loss of some kind. Or for example, if the height did not stop at H2, there was a different height it stopped at, or our kinetic energy initially wasn't V1, or whatever. There are a lot of different cases, or if there's a force that is being applied, and we will look at all of that today. So the total work lost is going to be the work from phase 1 minus the work energy at phase 2. So we can know how much work is lost due to this process. Okay? Yep, that's pretty much it. Any questions so far about energy before we start solving questions? These are the most important concepts I can think of for now. If I see anything else that we need to go over, I will go over it as well. But is this clear so far? Is there anything not understanding? Anything you want me to repeat? Okay. So again, the conservation of energy. شو معناته conservation of energy? Conservation of energy means any system you're going to have energy going in and energy going out, okay? Any system. What does this mean? That means that anything that is going in has to be equal to anything that is leaving the system. Think of it as water. زين, if you have a pipe, إذا عندكم ماء قاعد يدخل من هني، لازم الماء يطلع من هني. اوكي؟ ممكن يكون موزع، يعني ممكن يكون عندكم other two pipes like this. Okay? Something like that. One second. So something like this. يتوزع الماء، ولكن everything that is going in has to be equal to everything that is going out. This is what is known as the conservation of energy. Conservation of energy معناته any energy that we have stored in the system at point 1 has to be moved into the system at point 2. There is no energy that has been removed from the system يعني. The energy will always be existing here, whatever it was here. But in this case, if you notice, our potential energy has transformed into kinetic energy. This is what happened. لأن our potential energy, we had it available here as mgh1, but here our potential energy became 0 because it was falling, the ball was going down. So as it's going down at each phase, the potential energy is getting less and less and less and less until it reaches 0. And the opposite is true, because at the beginning, we had the velocity as 0. So as the ball is going down, the velocity is going up and up and up and up until it reached a point here where the velocity is at the maximum, and the highest velocity for this system at least. That is why our kinetic energy kept on increasing until it took all the energy from potential energy. This is what is meant by the conservation of energy. So it is going to be the total energy you have at a specific point, so phase 1. And that has to be equal to, so if this ball has moved into a second phase, wherever it is, the energy here has to be equal to the energy over here, whatever the values of energy is. So you will sum up your potential and kinetic energies here, and you will sum up your potential and kinetic energies here, and they have to both be equal to each other. The total value should be equal to each other, I should say. All right? Once you do that, then you can simplify by using half mv squared. And keep in mind here, this is still half mv1 squared. But in our case, it is equal to 0 because v1 is 0. All right? Same thing for potential energy. This is mgh, but in this specific case, it is equal to 0 because our h value is equal to 0. All right? This is the point. So here, this is why it is equal to 0. And for here, this is why it is equal to 0. Right? This is what is known as the conservation of energy. And when we're looking at it from the perspective of work lost, in this case, we don't have any work lost because everything is being transferred. But in some cases, you're going to have work lost, and we're going to solve a problem like that. And you will see that there's going to be a specific work loss due to a specific force or something else that is occurring as well, like a frictional force most of the time. Okay, now let us start solving questions so this concept can become a bit more clearer. Let's look at the worksheet. Okay, let's start simple. So, calculate the work done dragging a suitcase for 4 meters. So first things first, we have our moving distance. This is our moving distance. All right, which is 4 meters. D is equal to 4 meters. Along the floor, if the applied force, so the applied force is 80 newtons. So there's a force of 80 newtons that is being applied, and it's making an angle of 30 degrees with the horizontal. We draw this very quickly. So let's say this is the suitcase. It is being dragged across the floor, all right, with a force F, but the force is not straight. It is at an angle with the horizontal over here, which is equal to 30 degrees, all right? This F is equal to 80 newtons, and the distance that will be moved is from here all the way, let's say, till here. And this is where the box will be when moved, okay? So this distance is 4 meters. So what do we need to find? We need to find the work done. So work done is equal to force times distance. All right. However, here we have the force component. We have two components for this force. There's a force that is pulling it upwards, if you remember your force components. And then a component upwards. And we have another component. Let me keep it actually in the same color. That is on the right. Okay. So there's one along the y direction and one along the x direction, which is actually causing the movement. This force is just canceling out the force of gravity. It is not actually helping it move left and right. Tamam? So what does that mean? And this basically means that you need to find this component of force, which we will call our Fx. All right. So in this case, we're not looking at F. We are looking at F x times d. How do you find fx? If you remember from before, fx is simply equal to f cosine 30. So fx is going to be 80 cosine 30, which is going to be a value. All right. I believe it's going to be 40, right? No, it's not going to be 40 times 80. It's going to be 40 squared 3 or 69.28 newtons. So this is the force that we need to look at, our Fx force, because that's the one that is causing the distance, the movement of this distance. Therefore, our W is equal to 69.28 times the distance traveled of 4, which is equal to 277.128 joules. All right. Remember, our work and energy, the unit of it is joules. Very straightforward example. Very simple. Let's move on to the next one. Let's look at this question. So again, just before I move on very quickly, remember that work is simply just force times distance. But this force is the force being applied into the direction of where the distance is being moved. يعني it is parallel to the distance where it's moving. فهني, this force, Fx, is parallel to the distance that it is being moved through. All right? That's why we found the x component of this force. Let's look at the next question. So here, an 80-ton locomotive يعني just a type of train. All right. So 80-ton locomotive. So let's say mass of the locomotive is equal to 80 tons, which straight up is actually, before I do the conversions, let's continue reading the question. Hauls a train coaches of mass 240 tons. So there is a mass of the coaches اللي هم يعني الكابينات اللي ورا القطار, which are 240 tons. So in other words, if I want to draw this, it looks something like this. Let's say it has 3 cabins, and this is being pulled by a train. All right. Okay. So this is our 80-ton. And these 3 is our 240-ton. Okay. What do we need to do? We need to find this total mass. That's the first thing we have to do. We need to find the total mass of this train. So what do we do? The mass is going to be equal to ml plus mc. All right. So the mass is equal to ml plus mc, which is our total mass. So it's equal to 80 plus 240. M is equal to 320 tons. All right. Why am I finding the total? Because we need to, when we're analyzing, we're looking at the total energy that is being done or consumed or work done as well. And that you cannot find it for a specific part unless specifically mentioned in the question. But generally here, you're always going to be grouping up all your masses because we're going to treat this as a single object of 1 ton. So this is how it will be treated, as if this is a single object that is 320 ton. Okay. Now, where this is mass M. Now, before moving on, 320 ton is not in kilograms. Ton to kilograms, you just multiply by 10 to the power of 3 kilograms. grams. All right, so the first thing you're going to do is do the conversion. You guys should know that 1 ton is 1,000 kilograms. Up an incline of 1 in 80. All right, a lot of people get confused when they read something like this. An incline of 1 in 80. What does an incline in 1 of 80 mean? معناته, if they say an incline of 1 in 80, basically it means that it goes up 1, it goes up 1 for every distance 80 that is covered. Yani if I want to draw the triangle for this is going to be 80, all right? And this is going to be our 1. So this is the triangle that you have. This is what is meant by an incline of 1 in 80, all right? Simply, this is it. Now you can just apply your basic trigonometry, SOHCAHTOA, to find your theta value over here. You can do that using tan of theta, which is opposite, which is 1, over adjacent, which is 80. So your theta value is simply equal to the tan inverse of this number, which is going to be a very small number, 0.716 degrees. All right. A quick comment. If you remember yesterday's class, we were talking about radians. Here, we are dealing with degrees. So you have to make sure when you're solving a question where you're dealing with degrees, you have to make sure your calculator is also in degrees. All right. These are all the questions from the worksheets. Okay. So an incline of 1 in 80. This is how the point of finding it. So now we have our theta. So now we can calculate, like we can have the train on top of this and we can find our values and all of that. All right. Before even moving forward with this, let's see what the question says. We haven't continued reading the question. So it hauls a train coaches of this mass up an incline, a distance of 600 meters. So this is our moving distance. Or in other words, this is equal to D, which is 600 meters. The rolling resistance is 55 newtons per ton. So we can call this our friction is 55 newtons per ton. Remember, this is not being given in newtons directly. This is, I'm just actually going to call it friction T. So it's the friction per every ton. It is not the total friction. All right. If the acceleration is 0.1 meters per second squared, so our A is equal to 0.1 meters per second squared, find the work done. So we need to find work done. Okay. So what do we need? We need to find our work done, which is going to be equal to a force times our distance. Okay. This is what it is. We have our distance, but we do not have our force. And we're going to need to find that. How do we do that? So now we know the incline of where this is moving. We know the shape or the design of this. We know how it is going to be moving. So if I just copy paste this here, keep in mind that this is only to determine the angle. These aren't actual distances. All right. So this isn't actually 80 and this isn't actually 1. This is just a ratio to find your angle. So now what can we do? We can draw our free body diagram. So if we have our train, let's say this box is the train, there's going to be a weight W, which is equal to mg in this direction. There's going to be the force of friction that is going here. It's on the floor, but I'm just making it here so it's visible. This is going to be our friction force. And because this is accelerating, so remember we have an acceleration. What color did I do acceleration in? Purple. All right. So we have an acceleration going up equal to 0.1 meters per second squared. This means that we will have an inertial force in the opposite side. معناته we're going to have a force, let's call it F, which is equal to MA, that is acting on the opposite side. So let me actually put this on the body so that it is a bit more clear. So we have acceleration. This is our inertial force, just like last time. Remember, we're going to have an inertial force that is resisting the acceleration, all right, which is always in the opposite direction of acceleration. So let me call this FR so that we can avoid confusion. All right. This is, remember, just a general formula. This isn't actually this F. This is just a general formula. So let's call it, in this case, let's call it E times D, where E is going to be our total force. All right. So what does our E represent? Our E is basically this force over here, the force that is being applied that is making this locomotive move, أو هالقطار يتحرك. زين? This is our E force. If you remember how to do this, we need to find our sigma Fx. We have done this before. Sigma Fx equal 0. زين? Assuming that this is our x direction and this is y, يعني at an angle. Meaning E is equal, يعني I'm assuming this is positive and this direction is positive. E is going to be equal to, or I should say positive E minus the friction force Fr minus F minus, now it is not the complete weight. It is only the weight that is being acted on in, let me make this a bit longer. Second. So it is only the weight that is being acted upon in this direction. How do you find the weight in that direction? Let's call this Wx. Again, it is in the negative direction, so it's going to be minus, but it is going to be weight times, since we have already found our theta value, all right? This basically means that this angle over here, this is also our theta value, if you remember from mechanics, from before the midterm, all right? This angle is also our theta value. So Wx is opposite, so it's going to be sine. Again, revise your trigonometry from older sessions. I'm not going to go through them again here. So W sine theta, which is your Wx, okay? Let me actually write it as Wx here, and Wx is equal to W sine theta. And this all is going to be equal to 0. So the idea here is you're trying to find your E, right? We subtract Fr, F, and Wx from all of it because they're in the opposite direction. Now we can just plug in the values, but first let's rearrange a bit. Let's take everything to the other side. So E is equal to our friction plus our force, which is MA, plus our Wx, which is W sine theta, all right? Or even more simply, mg sine theta. Okay, so we have the value for m, which was 320 tons, yani 320 times 10 to the 3 kilograms. We had our acceleration. Our acceleration was given as 0.1 meters per second squared. Our g is going to be assumed as 9.81 meters per second squared. Our theta, we have found it earlier as well, which was 0.716 degrees. So what is remaining? So we have all of these. What is remaining is the friction. Now, if you remember in the question, the friction given was per ton. I called it Ft. So Ft was, Ft is equal to 55 newtons per ton. So for each 1 ton, all right, for each 1 ton, we need, there's going to be a friction of 55 newtons for each singular ton. Remember that our mass in tons is 320 tons. Yani if we had 1 ton, we're going to have a friction force of 55. So to find our friction force Fr, we are going to multiply 55 newtons per ton by our mass, which is 320, all right, tons. Because they're talking in tons here, so we're going to keep it in tons. This is our mass. If you notice here, our ton and ton will cancel. So our friction force, our actual friction force for 320 tons, not 1, is going to be 55 times 320, which is 17,600 newtons. And now we have all of our unknowns found. So we know that Fr equal 17,600 newtons. Now we can plug in to find our E value, which is our total force to accelerate the strain. So Fr, which is 17,600, plus m times a, which is 320 times 10 to the power of 3, times acceleration, which is 0.1. Remember, this has to be in kilograms. Plus mg, m is again 320 times 10 to the power of 3, times gravity, which is 9.81, times the sine of theta, which is sine of 0.716. Plug this all into your calculator. You're going to find the value for E, which is going to be equal to 88,828.17. So 88,000 roughly newtons. Okay? This is our E value, or in other words, this is the total applied force required to move the train 0.1 meters per second squared. So now we can find our work done. Okay? Now we can find the work done, which is equal to E times the distance D, which was given in the question, if you remember, as 600 meters. And now our D is equal to 600 meters. And we can find work done, which is equal to E times D, which is 88,828.17 times 600 meters, which you will notice now is going to be a huge value. So this will give me 532.96903 joules. Or if you want to convert this into a nicer number, we can say that this is 53.3 megajoules, all right? Because mega is 10 to the power of 6. Is it clear what I did here? Again, just a very quick recap. At the very beginning, we have found our total mass, all right? Our total mass, because they split the masses up for some reason. So it's just a trick to trick you. Just make sure you combine the masses. Up an incline, when they're talking about an incline, they're talking about this. So when they start with 1 in 80, and they do not mention anything after it, so they just say 1 in 80, معناته in an incline, meaning going upwards of 1, in the distance, a horizontal distance of 80, like you see here. Once you do that, you can find the angle. I saw a way they did in the solutions, which I did not like, so just follow this way. It will make it easier for you guys. Just find the angle. Once you find the angle, you can now apply your basic mechanics, all right, of summation of forces and equilibrium and all of that. You will know that you're going to have the weight downwards and the friction opposing the motion. And the motion is going to be upwards, which is E. And because we have an acceleration, there's going to be an inertial force going backwards or holding it back, which is MA. Then we're going to plug it all in our sigma fx equation. We're going to find out all the values using trigonometry. Make sure that the weight is just the weight that is being applied in the same direction, parallel to the distance that is being moved. All right. Once you find all of that, plug in all your values, and you're going to find your work done, which is equal to the total force required to move this, which is our E, times the distance that has been moved, and you'll find your work distance. For the friction, they gave us per ton, so the weight was depending on 320 tons. This for friction was for one singular ton. So if you want it for 320, you just simply multiply it by that number to get your total friction that is being applied for this locomotive. All right. The inertial force will always be present if you have acceleration. This inertial force is always there because of acceleration. Before, when we used to deal with it, there wasn't any acceleration. So that's why we never had this inertial force. Now, when we're dealing with dynamics, we are always going to have an acceleration. Therefore, there will always be a force or an inertial force due to the acceleration. All right. Moving on. I guess no one has any questions so far. Let's move on to the next question. So far, this wasn't a lot of energy questions. It was mainly work done questions. Let's take a look at some basic energy questions now. Where did the sheet go? All right. So, next question. Very simple and straightforward. So a ball is kicked vertically upwards. يعني شايطينه فوق vertically meaning it's going upwards in a straight line vertically. All right? With a velocity of, so our velocity v is equal to 35 meters per second. Determine the greatest height reached involving energies. So what do they mean by that? So first, you obviously, okay, you can just apply one equation to find it, which is going to be v is equal to the square root of mgh. You put your velocity here and solve it and all of that. But if you notice, you do not have your mass. So you cannot actually find it using this equation. So how do you do this actually? Very simple. The same exact concept I was speaking about earlier. So when you have an energy equation like this, where there is motion, always determine your first phase. So this is phase 1. And your second phase, this is phase 2, where the ball is stopped at the top, all right? Because it's the greatest height it reaches. The greatest height is basically when the ball stops before it starts falling down, all right? So this is going to be our phase 2. So phase 1, we know the velocity is 35 meters per second. Let me change colors. All right. So this is V1, which was equal to 35 meters per second. The height here is going to be considered as 0 because this is our reference height. Usually when we're talking about heights, we're talking about the reference height. So h here is going to be equal to 0 meters. All right? I don't know why I did it in green. So our h1 is equal to 0 meters. At point 2, remember, this is when the ball stops. In other words, velocity 2 is going to be equal to 0 meters per second. And our height is now equal to a specific value that we need to find. We'll call it h2. So how do you find out what the value of this height is? Very easy, very simple. You apply your conservation of energy. So you're going to have your K E2 is equal to 0 and your PE2 is equal to mgh2. All right, this is why I said you guys need to know these equations by heart. Same thing again, you're going to apply for the bottom ones. So KE1 is not equal to 0 because we have a velocity, so half mv squared or mv1 squared. And potential energy 1 is equal to 0 because our height is 0. All right? معناته if we want to do our conservation of energy now, conservation of energy. معناته energy is being fully transferred. We're going to take our phase 1 and it has to be equal to all the energies in our phase 2. In phase 1, our potential energy is 0, but our kinetic energy is there. So kinetic energy 1 is equal to. In phase 2, our kinetic energy is 0, but the potential energy is there. So it's equal to potential energy at 2. All right. This wouldn't always be the case, but in this simple example, it is where you have 0 and 0 for kinetic in one phase and potential in the other phase. And now you just plug in values and you're done. So you have for kinetic energy first, we have half mv1 squared is equal to the potential energy, which is half. Sorry, it's not half, it's mgh, all right? I got lost in a second in my head. So mgh2, all right? So you have half mv squared and mgh2. If you notice here, like previously, the masses will cancel. And then you can use this equation to determine the height that you needed. So we know that half, let me actually remove all the colors now. So we have half v1 squared is equal to gh2. We remove the g to the other side. You're going to have h2 is equal to v squared over 2g. All right. This is another form of the equation that I said earlier, which is v is equal to square root of 2g h. You can just apply this equation directly because you have the height and or you have the velocity and you have obviously gravity, so you can determine the height directly. The reason I'm doing it using the full method is because later on, maybe not even in this in today's session, but tomorrow's session, when we're talking about energy, there will be a lot of cases where your kinetic and potential energy are not equal to zero. All right. So moving on, this is going to be equal to v squared. We know our velocity is 35 squared over 2 times 9.81. Therefore, our height is going to be 35 squared divided by 2 times 9.81. اللي بيعطيكم 62.44 meters. All right. Is this clear? Let's look at another similar example. So, we have a drop hammer which is allowed to fall from rest through a height. What is a drop hammer? A drop hammer is a thing that is usually used for forging. عادة يكون عندكم something like this, okay? زين, and then they put like some pieces of metal here, a piece of metal here, whatever it is, and then there's usually a plate here to hold it, and then you're gonna have something like a hammer over here. زين? Something like a hydraulic press if you've ever seen it before, but the difference is this is an actual hammer that is dropped down. Yani it's completely released. It's not gradually released. Okay? So this will fall down on the workpiece and it will forge it or shape it or whatever the process is in this case. All right? So a drop hammer is allowed to fall from rest. So our first phase, which is before the hammer dropping down, let me just draw it as a single line so it's easier. So we have our hammer here, all right? The hammer is going to be dropped down. In our first phase here, velocity is equal to 0. So V1 is equal to 0. Through a height of 6 meters, but our height H1 is equal to 6 meters. All right? Because we know that this total height is 6 meters. Onto a forging. Find the downward velocity of the hammer when it strikes the forging. So we have when it strikes the forging, phase 2, all right? So here, this is when it hits. Here, our height is now 0, but we have a velocity 2, but our height 2 is equal to 0. Since you have this common or general form, you can directly find your V2 is equal to the square root of 2GH1. You can directly find it using this way, or you can apply the same method with conservation of energy. I just wanted to use it one time in a question so that you guys can see how it is used. All right. So once you apply it, you can find your V2 is equal to, so V2 will be equal to square root of 2 times 9.81 times H1, which is 6. V2 is going to be 10.85 meters per second squared. All right. So this was the first part, which is finding our velocity. Now, if the mass of the hammer is 500 kilograms, so now they're telling us that there is a mass for the hammer, right? It is equal to 500 kilograms. What is the work done by the forging and base plate in bringing the hammer to rest? In 50 millimeters. So you have two things here that you need to look at. The first one is the forging, which is this case over here that we're looking in front of us, going from 1 to 2. And then there is another case of the base plate, which is the base plate down here. This is our base plate that will stop the hammer from moving, but it will cover a distance of 50 millimeters, or in other words, 0.05 meters. All right. Before I continue this question, I really need to take this phone call. So I will continue this question. I'll repeat it from the beginning. Let's take a 5-minute break. All right. Let's make it a 10-minute break. And I will re-explain the question. Sorry about it. So break, and we'll be back at 5:15. All right. And we will continue solving. Okay, sorry about that. Let's redo this question from the beginning again, very quickly. You knew how I got the velocity. I just applied this equation. It was meters per second, not meters per second squared. Again, you can either apply the conservation of energy completely, or when you have this specific case where you have a height and one velocity only, you can just apply this equation to find it. Now let's talk about the work that is being done. We are given the mass of 500 kilograms, all right, for the hammer. So the mass of this hammer that is falling down. What is the work done by it for the forging part? The forging part is this first part over here that we have already found the velocity and the potential energy and the kinetic energy and all of that. Okay, so the work done over here is equal to the potential energy going from all the way up until the bottom. Okay, which is also equal to the kinetic energy at the bottom. Because remember, work done is going to be equal to the kinetic energy, right? We're not talking about work loss. Work done is equal to the total energy. So in other words, we're talking about the total kinetic energy plus potential energy at one point. At one point. So at either one, or you can say it's also equal to the kinetic energy plus potential energy at point 2. Because this is our conservation of energy equation, right? Kinetic energy plus potential energy is equal to this. And the energy is always equal to the work done. So they're all equal to each other. So we can find the work done by simply finding the potential energy at 1. All right? This is for the first part. This is for the forging part, all right? The initial part, which is by the forging. So let's look at this one first. Work done here, I'll call it work done forging. So WDF is mgh, which is equal to the mass is now given. So it's 500 times the gravity times the height, which was also given to be 6 meters. And this is our first work done for the first phase. All right, this isn't the total energy. This is just the energy for the forging, or the total work done for the forging part. Okay, which we get 29430. So 29430 joules. So this is for the forging part. Now, let's look at what the base plate meaning is. So the base plate in bringing the hammer to rest in 50 millimeter. So if we have the hammer already at the bottom, all right? So it's at the base plate. Okay? This base plate over here, it's gonna go downwards until it reaches this point, basically. And this distance is a very small distance of 50 millimeters. It's basically absorbing work, so it's doing work to absorb the impact force from the hammer. So the work done, the distance now is going to be equal to 0.05 meters or 50 millimeters. So now we're talking about base plate. Okay. So this distance, or this is also known as, you can call it height B, is 0.05 meters because it's a height, right? From here to here, this is a height. It's a vertical distance, or we call that usually height. So for the base plate, the work done by the base plate is going to be equal to the potential energy at the base plate. I'll call it PEB. And that is equal to mgHb, which is equal to just the mass that we have already found or given, 500 times 9.81, which is gravity, times the base plate distance that is going to be covered, which is 0.005. And now we can find our WDB to be equal to 500 times 9.81 times 0.05. That gives us 245.25 joules. So now we have found our work from the forging and the work from the base plate. Total work is going to be equal to W work done by the forging plus the work done by the base plate. Just add them up. It's the total work. So it's going to be equal to 29430 plus 245.25. Therefore, our total work is going to be 29675.25 joules, or you can say that this is 29.68 kilojoules. All right? Because this is in the thousands, we can just make it simpler like this. This is not a requirement. As long as you know how you got this, this is all that is needed. All right? Is this clear? So far, it's pretty easy, pretty straightforward, nothing too complicated. Let's look at the last question from this worksheet. Question number 5. There it is. This one is very easy, very straightforward. It is similar to question number 4, but here you have much less work required to do. So here they're saying the same thing. A drop hammer is raised to a height of 3 meters above its striking point and then released. So you have the drop hammer, and then the height from here to here is 3 meters. All right? Calculate the velocity at the instant of striking. So again, if you're doing it phase-wise, phase 1, your height is equal to 3, but your velocity is equal to 0. And phase 2, هني, the height is equal to 0, and your velocity is equal to some number that we need to find. And you can simply just apply the formula, which is V is equal to square root of 2GH. So V is going to be equal to the square root of 2 times 9.81 times height, which is 3. So this will give us a value of 7.67 meters per second. And that's it. That's pretty much it so far. Anyone has any questions about this before I move on to the second worksheet? Feel free to ask. شكل عالي يمكن كنسله لأن أنا I downloaded everything from the beginning of the semester, so maybe I have all of this from the beginning of the semester. Either way, the concepts that we are going to be doing similar concepts. يعني إذا فهمتوا كل اللي سويناه هني, this is just basic information. اللي بنسوي بعد يعني in the second worksheet we're going to be applying the same concepts all over again. All right. خلنا الحين we will do worksheet 2, no worries. Why didn't we calculate KE? We could have calculated KE, but remember, what did I say? Our WD is equal to KE1 plus PE1 or KE2 plus PE2. يعني, you could have found, instead of WDF equal PE, you could have said WDF is equal to KE2. All right? Then it's either this part or this part. It's equal to each other because of the conservation of energy. Yani you could have used half mv squared, where with the velocity we have calculated here, and you would have gotten the exact same answer. This is the idea of conservation. هني, this KE is equal to 0. And just a reminder, this is 0 and this is 0. That's why. And technically you would do KE1 plus PE1. But since KE1 is 0, it's just going to be PE1 equal to the work. Or you can use the second phase where kinetic energy is there and you can have the value here, but the potential energy is 0. All right. Is that clear? Whoever asked this question. Let us go on to the second worksheet. بس قبل ما أبدأ أحل عشان أتأكد وياكم, this is the worksheet that you guys have, right? The second worksheet. A car of mass 1125 and then a car of mass 1000 descends a hill, 1 in 5 sine, 1 in 6 sine. Is this the same worksheet that you guys have? Okay, tamam. Let me start solving this one then. All right. Again, it is this yani energy is not that difficult. It's not like the torque that we did last time or circular motion. It's very straightforward. You just need to understand the concept, understand the question, and just apply. So let's start doing that for worksheet 2 now. So the first question is this. a car of mass 1,125 kilograms. All right. So we have mass of the car is 1125 kg. Descends a hill of 1 in 5 sine. All right. So early on, we saw 80 or 1 in 80 or 80 in 1 or something like that. But there was nothing written after it. In this case, it is written sine. What does sine mean? It means that if we are going to draw our triangle, it means that this is your angle theta. And what is sine? Sine is, if you remember, sine the SOHCAHTOA. So sine is opposite over hypotenuse. So it means that this is going to be your opposite of the angle, and this is going to be your hypotenuse of the angle. In other words, this is going to be your 1, and this is going to be your 5. You can directly, without even drawing, you can directly just find it from here by saying, okay, theta is going to be equal to the inverse of the opposite, which is 1, over the hypotenuse, which is 5. This is what is meant by hill of 1 in 5 sine. When nothing is mentioned, it means the same concept but tangent, all right, which we saw earlier when nothing is mentioned. But either way, if it's mentioned sine, this is how you would find your angle by doing the sine inverse of 1 over 5. All right. Yeah, that's pretty much it for this hill, the hill. So now you have your angle. You know how much your angle is while it's going up. Calculate using an energy method the average braking force required to bring the car to rest from 72 kilometers per hour in 50 meters, step by step. So what are we required to find? We need to find our braking force. So let's call that FB, which we don't know yet. All right. Required to bring the car to rest from 72 kilometers. So first, a car of mass is descending. So we know that the direction of this car is downwards. So if I redraw this, the car is going in this direction. Yani in other words, acceleration is here in this direction. Okay? So it is descending. Well, actually, it not necessarily has an acceleration, but yeah, definitely does because the velocity is changing. But in other words, معناتها it's going downwards. We do not need to know acceleration, so I'm just going to call this motion. All right, the direction of motion. It is going downwards. Okay. So, all you need to know here is you need to know your phases. What are the phases that we have? So this is first phase, and then this is our second phase. And it's going downhill, and this is angle theta, which, by the way, I don't think we're going to be using in this question. But we're going to have our phase 1 and phase 2. Let's understand what this car is starting from and where does it end. So it starts from 1. The average braking force required to bring the car to rest from 72. So it says from 72 to rest, meaning V2 is equal to 0 and V1 is equal to 72 kilometers per hour. So V1 is 72 kilometers per hour. A quick way to convert this into, obviously you have to convert this into meters per second. A quick way is by dividing by 3.6. So V1 will be equal to 20 meters per second. And then, now, V1 is equal to 20 meters per second, meaning we have here V1 is 20 meters per second. And obviously, we're going to have a height here. All right. We're going to have a height here that we still have not found, and we're going to look at in a bit. So H1 is equal to a value, and we're going to look at that in a bit. But first, let's finish with our velocities. The average braking force required to bring the car to rest at V2. So here V2 is equal to 0, and our height is also equal to 0 in this case. So H2 is also equal to 0. All right. So phase 1 is our only phase where we have a velocity and a height. But how can we find this height? This is why we used this relation in the beginning, because they told us that the distance is 50 meters. Yani this is basically the braking distance. In other words, this is this distance over here, or not the braking distance, but distance to brake into. Yani the average braking force required to brake the car in 50 meters. يعني توقفون السيارة in 50 meters. So we know that in this triangle, this is 50 meters. So if I redraw this triangle now, then not to scale, obviously, this is our 50 meters. And this is our height, h1. And we have an angle theta over here. How can we find the value of h1? Very simple. So katoa. We have opposite and hypotenuse, so we're going to be using sine. Sine of theta is equal to opposite, which is h1 over 50, which is the hypotenuse. So now we have the angle theta, but we need to find this in terms of h1. So h1 is equal to 50 sine theta. And theta, we calculated it earlier. Actually, I didn't do the calculation, but it is sine inverse of 1 over 5. Theta is equal to sine inverse of 1 over 5, which is 11.54. All right, that is our angle. So down here, I'm going to write, instead of sine theta, I'm going to write sine of 11.54. Make sure your calculator is in degrees. h1, which is the height that we need to find, is equal to 50 sine 11.54, and that will give us 10 meters. Okay. There is another way of finding this height without calculating the angle, but that usually causes a lot of confusion for people. But it can be done through ratios, meaning that this is a ratio of 5 to 1. معناته if we have 50 here, this is going to be a ratio of 50 to 10. Because if you divide 5 by 1, it is equal to the division of 50 over 10 meters. All right? So I'm just going to put this as a side note. This is ratios. If you want to use it through ratios, I do not recommend using ratios if you don't understand it, because you'll get confused. But you have 5 over 1. It has to be equal to 50 over h1. This is what is meant by these ratios. It's the same location. This is the height and this is the hypotenuse. This ratio has to be equal to this ratio. And then you can find your h1 by doing cross multiplication. So it's going to be 50 times 1 divided by 5. So h1 is equal to 10 meters. All right. This is just a different way of solving without using sine. If you understand it, you can use it. If not, stick with this because you guys practice this a lot, and just move on with that. Now, I'm going to move this actually down here, make it a bit smaller if you want to use this method. So, so now we found our height, we found our velocity. What can we find? What do we need to find? We need to find the braking force. We know that the braking force is going to be work done is equal to the braking force times, it's not going to be the braking force, it's going to be E, the total force, times the distance that it has moved, which is our 50 meters over here. We have our distance, all right? So this distance, we have it already, but we need to find our E first, all right? Before even moving into this, we don't even have the work done to manage to find the value of E. So how can we find the work done? We have our energies. We have our potential and kinetic energy. Our second equation for work done is equal to KE plus PE for one phase. So I'm just going to write 1. Okay? So in other words, the work done is equal to kinetic energy is half mv squared plus potential energy is mgh, and we're talking about v1 and h1. If we plug in the values of v1 and h1, we have 20 meters per second for v1 and 10 for h1. So it's half. The mass was given 1125. Yes, 1125. The velocity is 20 meters per second plus and we're going to square it, plus mgh, which is, again, the mass, which is 1125, gravity, which is assumed to be 9.81, and the height of 10. So the work done is equal to, so again, this is equation 2, right? And this is equation 1. All right? So the work done, we found it from this equation. It's going to be half times 1125 times 20 squared plus 1125 times 9.81 times 10. That gives us 335362.5 joules. Now we have found our work done. We can plug it in back into equation 1 now to find out our E value. All right? So, in other words, now if we look at, so plug into equation 1. All right? Equation 1 was WD is equal to E times D, which is 335362.5 is equal to E, which is our total force, times the distance, which is given to be 50 meters. صح كان 50? Yes, 50 meters. So we know that our E is equal to 3362.5. We're going to divide 50. 6707.25 newtons. What is this E value? So if we draw again here our slant, this E value now, all right, is going to be our frictional, our force that is holding the braking force. So if we are braking, معناته the force of braking is going to be going into this direction, in the direction of friction, because remember, motion is in this way, all right? Let me color code this so you guys don't get confused. So we're going to have our FB, our braking force, and we have our friction, and our motion, our E, is going to be on the opposite side. Okay? E. All right? This is where the motion is occurring, and we want to brake, apply a braking force to stop this motion from occurring. So our sigma fx, let's say that this is our x direction, and let's say this is positive and that is negative. And that's positive y. So this is y and this is x. معناته equals 0. In other words, our E is equal, or E minus FB minus FR is equal to 0. All right? In other words, معناته the friction force is helping out the braking force. All right? Let me make sure my directions. I feel like I did something wrong here, but I'm not sure. What was the value of friction given? We were given friction is 250 newtons. All right? Let me just double check again my work, just in case. Yep, all right. So, again, so this is our free body diagram. This is our equation. Now, our E is going to be our total E is equal to, or actually, we don't care about E. What are we trying to find? We are trying to find FB. We want our braking force. So FB is equal to E minus FR. All right, so I just moved FB to the other side, and we will be left with E minus FR. All right, so in other words, it is equal to 6707.25. And remember, our friction force was given to be 250 newtons. So minus 250. Our FB, our braking force now, is equal to minus 250. It's going to be 6457.25 newtons. All right? Or you can say that this is equal to 6.46 kilo newtons. Okay. This again, this is basic mechanics. Yani all of this solving down here, this is just sigma fx and all of that. This is just stuff you already should know. Okay. The trick is knowing how to use these two equations. Work done in terms of force times distance, moving distance, and the work done, which is the kinetic and potential energy summed. All right. Question 2, I'm going to skip because it is very similar to this concept. The one difference I believe is now you don't have rest here. You're going to have an actual velocity, but the solving of it is exactly going to be the same with minor changes only. So I'm not going to go over that. So I can do question 3. Let's do question 3. So question 3 says, a piston of a reciprocating engine moves with an approximately simple harmonic motion. What does this mean before I even go through the question? So a piston then looks something like this, right? And these are going to be the walls of the cylinder, then, and the motion of it is it goes up and down, and it is connected to something known as the crank shaft. All right, اللي هو بيكون excuse my drawing, but it's going to look something like this, and then it's going to be connected to the left, to the right. Okay, and then it's going to be connected to another element over here, and then another shaft like that, and then this shaft is connected to another shaft in the middle over here. All right, so it's going to look something like this, and this is the center. This is the center, and this rotates around. Yani this middle piece, it keeps rotating in a circular way, and as it goes in circles, the piston keeps going up and down. All right, so this will have an angular velocity, but the piston will have a linear velocity. معناته the piston will have v, but this will have omega. All right, and if you remember your relations between omega and v, since they are connected, v is equal to omega times r, the radius. All right, so this is what is known as the crank or crankshaft. And then the crank speed is 1440 RPM. So we have our omega is 1440 RPM, or in other words, it is equal to 1440 times 2 pi over 60 radians per second. Remember from yesterday's session, we need to convert this into radians per second when we want to use it into calculations. So our omega is going to be equal to 48 pi radians per second. All right, I like to keep the pi just to be a bit more accurate. Now, this we are done with. So we got our angular speed, and the crank length is 150 millimeter long. So the crank length, meaning this length over here, this length, the length of this. All right, so this is our length L, which is equal to 150 millimeters, or directly convert it into meters, it's 0.15 meters. If you notice, like I said, this is the thing that is rotating. So if we're looking at our shaft, this is going in a circular motion, all right? This is going in a circular motion, meaning, let's say this is the center, meaning that this is also our radius. The length of it is also equal to our radius, which is 0.15 meters, because this is following a circular motion around the center point over here, right? So this keeps rotating like that, meaning this is going to be our radius. This is also the distance that is being moved, which we will see in a bit as well. But why do we want the radius? Because we want to find our linear velocity. So now we can say that V is equal to omega r, which is equal to 48 pi times the radius of 0.15. So our V is going to be equal to 7.2 pi meters per second. Again, you can just convert it directly to 22 or something like that, but I like to keep pi over here in my calculations. Why did we find our velocity? What's the point of finding our velocity here? The reason we need to find velocity is if we read on in the question, if the mass of the piston is 5 kilograms, so we're given the mass is 5 kilograms, find its maximum kinetic energy and the force required to bring it to rest. All right, so we need to find the maximum kinetic energy, meaning that we need to find half mv squared. That is why we are finding our velocity. And then we're going to have to calculate the force to stop this motion, to get our v to be equal to 0. All right, so one step at a time. So now that we have found velocity, we can say that the kinetic energy is equal to half mv squared, which is equal to half. The mass was given to be 5 kilograms. Velocity is 7.2 pi squared. All right. Now, kinetic energy, or the maximum kinetic energy, you could say, is going to be 7.2 pi squared times 5 times half, which is 1279.10 joules. All right. So this was the first part. We have found our kinetic energy. Now, what do we need to also find? The force that will stop the motion, the force required to bring this motion to rest. How do we do that? Again, remember, when we are talking about force and energy, we know that work is equal to force times distance. All right, this is our first equation. Our second equation is work is equal to kinetic energy plus potential energy. This is our second equation. If we look at the piston has two energies. It doesn't have just one. It has both kinetic and potential. Why? Because it has a specific height over here, all right? Or it covers a specific height, I should say, all right? So it moves from here to here, this height, and let's do the connections very quickly. This is what it looks like. Okay, and it also has a velocity, so it has both a height and a velocity, because remember, this piston is moving up and down. It keeps going up and down, meaning that meaning that we have both kinetic and potential. So what is this height? How do we know the value of this height? So remember, when this is moving in a circle, right? Let's try to make a better circle. So when this is moving in a circular direction, the height of this, when this reaches a point down here, let's color code it so you guys have a better understanding. So when it reaches a point down here, all right, this is going to be pulled all the way down till here. All right, well, when this moves, the shaft is moving, and now it is connected here. This is going to be pulled down. The piston is going to be pulled down all the way till here. And then when it goes all the way back up, it is going to be going all the way back to the original initial height that you have. This is what is meant. Yani, this will look something like this. Yani, this will be connected here, and then this will be connected directly here. Because this shaft is going to be flattened out, so it's going to pull down the piston. All right? Therefore, this height is equal to the height that we have of the shaft over here, which is our L. So H is also equal to L, which is 0.15 meters, the length of the shaft that we have. Because this moving all the way from up to down, basically the size of it is how much the piston will go from up all the way to down. Okay, so that is why this is also our height, and we have potential energy. Our velocity, we have already calculated the entire kinetic energy actually, and we have it. Now we can find our work done from the second equation, which is kinetic energy that we found earlier, 1279.10, plus potential energy, which is mgh. So m is the mass. The mass is where was the mass? 5 kilograms. 5 kilograms times 9.81 times the height that we have found, which is 0.15. So our work is going to be equal to 1279.10 plus 5 into 5 times 9.81 times 0.15. It's going to be the total work done is going to be 1286.46 joules. All right. So this was our first equation. Now we can find the force from the first equation. So by plugging in back, we know that force is now going to be equal to work. Let me write it from the beginning. So work is equal to force times distance times the moving distance. معناته the force is going to be the work over the distance, which is 1286.46 divided by 0.15, which we have already determined to be our moving distance. So our force is going to be, right, by 0.15, 8576.39 newtons. Okay, clear? Work done is equal to loss in energy between 2 points. Work done is not the loss in energy. Work lost is the loss in energy. Work done is the energy available at each point. So the work done is basically the energy that is at this point and the energy that is at the other point. It is not the difference of energy. That is the loss of energy. That's two different things. Work done is energy. All right. Work loss is loss in energy. So do not get confused between those two. And I believe we're going to see that a lot in in question 1 and 2. We used the work is equal to energy. We didn't use work loss. There was no loss so far. We did not look at any work loss. Here, we looked at, in this question, work done is equal to, where did I do it? Here, work done is equal to kinetic plus potential energy. In worksheet 1 as well, we did the same thing. The total work done, where was it? Here, the work done is equal to the kinetic plus potential energy in phase 1, which is also equal to the kinetic and energy and potential energy in phase 2. This is what the work done is. It's just the total energy or the total work that is being done. All right? Work loss is a different thing completely, which I talked about. Work loss is different. All right? Work done is basically the entire energy that is available in the system at a certain point. So this is kinetic energy 1 plus potential energy 1. This is what the work done is equal to. This will always be the case. Okay? Sometimes if we will see that actually in the next session, so you don't get confused when it comes to impulse and momentum. We're going to see that a bit more there. So I don't want you to get confused. In this case here, when we're talking about kinetic and potential energy, the work done is basically the sum of the kinetic and potential energy at a specific point. All right. Let's continue on with the next question. This question was a very interesting question. So, a space module of mass 185 kilograms is near the surface of the Earth. So step by step, we are given a mass of 185 kilograms. And it's near the surface of the moon. So our gravity is even given. Gravity is no longer 9.81. It is 1.6 meters per second squared. When its twin retro rocket fire to enable it to make a steady vertical flight. What thrust is needed from each rocket? So, عندنا, I'm not going to draw a proper rocket ship, but let's say this is our rocket ship. And just to make it look a little bit more like a rocket ship, okay, it has its wings where there are thrusters here. These thrusters have a thrusting force that is pushing it upwards. So let's call this F thrust, like force of thrust, right? And they said they have two of them, all right? They said when it's twin retro rockets, meaning there's two thrusters, one on each side. And the question says, what is the thrust needed from each rocket? So we have to consider these as separate entities because we want to find the thrust for each rocket. If not, we are just going to put one FT anywhere and that's it. But in this case, we need to consider each rocket by itself. That's why we had a thrust force for each one. Okay? And what do we always have? We have weight. W equal mg. So what is going to be our thrust force? Simply, it is going to be sigma Fy equals 0, meaning 2, or let me just do it step by step so you guys don't get confused. So Ft plus Ft, the thrust force for both, minus W is equal to 0. In other words, 2 Ft is equal to mg. In other words, Ft is equal to mg divided by 2 for each rocket, which is the mass that was given 185. And the gravity, make sure you are putting 1.6 because now we are on the moon, not on Earth. So our gravity is different. Therefore, Ft, the thrust force for one rocket, all right, is just simply 185 times 1.6 divided by 2. This is very simple. There is nothing to do with energy at all here. This has nothing to do with anything after the midterm. This is all from before the midterm. You should know how to find this. So this is 148 newtons. Now, they say if the module rockets have to accelerate it vertically upwards, معناته from rest on the surface, at an acceleration of 3 meters per second, what thrust is needed for each rocket? So now in this case, then let's say this is the moon, all right? A very small moon. And let's say this is our rocket, okay? Our rocket is here with its thrusters, and it's at rest. So meaning V0 equals 0 or U equal 0. Tamam? Let me actually say U is equal to 0. So our U here equal 0. Tamam? And we know we have a vertically upward acceleration A of 3 meters per second squared. Then, we know that we have our thrust force that is required here that we will find in a bit, Ft and Ft, and we have our weight, which is pulling this down on Earth or on the moon, W, which is equal to mg. Okay. The question says that if the model rocket has to accelerate vertically upwards, like I said, from rest on the surface, what is the needed from each rocket? So we have one more thing, because we have acceleration over here. We are going to have ma in the opposite direction, our inertial force F equal ma in the opposite direction, because you have acceleration wanting to go up. So this is the inertial resistance to the acceleration. معناته now our sigma Fy is equal to, we have equal to 0. So upwards is going to be positive. So we have our thrust force plus thrust force minus F minus W equals 0. In other words, 2Ft is equal to Ma minus mg. Right? So Ft is going to be equal to Ma, the mass, times the acceleration. What was the mass? 185. So 185 times the acceleration of 3 meters per second squared minus mg, which is 185 times 1.6 meters per second squared, which is the gravity on the moon, divided by 2. All right, the 2 that was on the left side, we took it here. And this is going to be our new thrust force that we need for this to take off from rest. All right, because we have a specific acceleration, we have to consider our inertial force F equal MA. So this is going to be 129.5 newtons for each rocket. Each rocket. If you want to find total thrust force, you're going to multiply by 2 because you have 2 rockets. All right, very simple. Now, let's continue reading on. Calculate the kinetic and potential energy of the module after 10 seconds from rest. So, الصاروخ اللي عندنا إياه is now taking off from rest. All right, it is going into another phase over here where it has took off. This is our phase 1 and this is our phase 2. And the time it took to go from here to here, time was equal to how much was it? 10 seconds. 10 seconds. Yep, after 10 seconds. We know that it started from rest, so U is equal to 0, or V1 is equal to 0. And here we have V final, or just V2. Okay? And we have our acceleration as well, upwards at 3 meters per second squared. This is simply just linear. We need to find our V final, right? So this is very simply just linear motion that you can apply V is equal to U plus A times T. Okay? This is to find your velocity. So V is going to be equal to, our U is 0 plus 3 times 10, which is V is going to be equal to 3 times 10, which is 30 meters per second. So we have found our final velocity. We can find our kinetic energy. But the question, what does it say? It says calculate the kinetic and potential energy of the module. What do we need for potential energy? We need to find our height. Or in other words, we need to find the distance from here to here. Our S, in other words, our displacement. Again, this is linear motion. So we can use our S equation, which is equal to, you can use any one of them. I like using the average of velocities, so it's going to be V plus U over 2 times the time T. So in other words, this is equal to velocity that we have found, 30 plus 0 over 2 times 10. So our S, which is also our height, right, is equal to 30 over 215, 150 meters. Now that we have found our V and we have found our S, or our height, simply we can just say kinetic energy is equal to half mv squared, which is equal to half the mass. كم كان الماس؟ كل شوي أنسى. 185 times the velocity that we have found squared. And then the potential energy is equal to half, or mgh, or in this case you can say it's mgs, because s is our height. All right, so it's equal to 185 times 9.81. Actually, it's not 9.81. It is 1.6, because we're talking about the moon. So our potential energy is also gonna change. And the height, S, which is 150 meters. Put these both in the calculator and you have found your energy. So this is going to be 83,250 joules. And that one's going to be 44,400 joules. Clear? MA plus MG, same direction. Yeah. Oh, this is in the same direction. My bad. Oh, I put it as minus. This should be plus, plus. My bad. You're right. Because when you're taking F and W to the other side, they become plus. So this value is actually not this value. It is 185 times 3 plus 1.6 divided by 2. It is going to be 425.5. بالمنطق يعني, it has to be larger, much larger than this. It cannot be smaller than this, because this is just for the the rocket to fire while in space. Here you want it to accelerate. And when you have acceleration, you need a lot more force, a lot more thrust force, so for it to move upwards. That's the idea. And that's pretty much it. The last question, I wanted to solve it, but unfortunately lack of time. I'm going to go through it very, very quickly. وين راح الحين? Because there's only one trick at the end. I have already solved the exact same question with you guys in the last session. Almost the exact same question, I should say, which is this one. I'll just go through it very quickly, all right? So a cage of mass 4 ton is to be raised with an acceleration of, so we have the cage mass, so mass of the load is equal to 4 tons. Raised with an acceleration, so our acceleration is 1.5 meters per second, and we already know all of our directions. We know that we have a pulley, we know that we have a load down here, we know that we have an acceleration going upwards, so we know that there's going to be torque here, and there's going to be an alpha here, which is our angular acceleration, and opposite to this is going to be our I alpha, which I think we're going to neglect later on, and we have friction, T friction. This is the center point, and this is our radius. Here we have our E, which is the total force. Then, because acceleration is upwards, we're going to have our inertial force F equal ma downwards. And the reason I'm going very quickly through this is because I went in details last time. And then we're going to have our weight down here. And this is our mass of the load. Here we're going to have the mass of the drum. All right. Mass of the load is 4 tons, which is 4 times 10 to the power. Actually, let me just write it as 4,000 kilograms. All right. We convert it to kilograms. Over a hoist of drum, diameter is 1.5 meters. معناته our radius is 0.75 meters. What is the power required? I haven't talked about power, and I'm going to just comment on it in a bit. When the load has reached a velocity of 6 meters per second. أحس حلينا بالضبط نفس السؤال آخر مرة. So the velocity will reach 6 meters per second. All right. Neglecting inertia of the drum. All right. So here we are saying that I is equal to 0. معناته we are not going to look at our I alpha. We are going to remove it from our equation. Then now we are assuming I is equal to 0. Neglecting the inertia of the drum and the weight of the cable, and the weight of the cable. So the cable is, usually we are neglecting it anyways, but allowing for a bearing friction torque. So we do have a bearing friction torque of 3 kilonewtons. 3 kilonewtons, meaning we have 3,000 newtons. All right. What is the power required of the velocity? So the first thing you guys can analyze is you can analyze the load. All right. If you remember, we're going to look at the load very quickly. Sigma Fy equals 0. And that means that our E minus F minus W is equal to 0. معناته E is equal to F plus W, which is MA plus MG. And we have all the values, and we can find E. This is the first thing you're going to do. All right. So you find the value for your E. Now we are going to be doing what we need to find is our torque. So we have found our equation from here for E. So now we are going to do sigma moment. So this is for load. Now this is for drum. Sigma moment at point O equals 0, like we did last time. Let's call this point O. Let's take clockwise as positive. معناته our torque, our torque is clockwise. Everything else is counterclockwise because this load is pulling it downwards, and the friction is opposite to the torque, so it's going to be minus friction minus E times the perpendicular distance, which is our radius R. Okay, equals 0. Again, we have our TF, we have our E, we have our R. We can find our T by doing TF plus ER. All right, this is E times R. All right, E times R. Now that we have found our torque, this is where things change a little bit. So this velocity was given to us. What are we required to find? We need to find power required. All right. So the torque is going to be value-wise, I believe it's 36930 Newton meter. At the end, this is the answer you're going to get. Again, the application is very simple, just like we did before. So this is the torque that we got. Why are we looking at torque? When we look at power, insane. I didn't talk about power and I wanted to, but I forgot about it, to be honest. Power is simply energy over time, or work done over time. This is what power is, and the sign or the unit of it is watts. Okay, so power is equal to energy over time, or work done over time. In the case of rotational energy, the power, or you could say, let's look at energy or work done first. So work done is equal to force times distance, right? This is for linear. For linear, we're talking about a linear distance. What about angular? What do we replace distance with in angular? It is going to be F times, actually instead of force, we're going to be talking about torque because it's going to be angular, and the distance will be theta. All right? This is the change that happens when you are looking at work done in the angular form. So remember, power is equal to work done over time. So in angular form, it is going to be the torque times theta over time. Or in other words, theta over time is equal to omega. The change of displacement over change of time is equal to the angular velocity. So we can say that power is equal to the torque times omega. Again, the derivation is not important. What you need to know is power is the torque times the angular velocity. So now going back to the question says we have a velocity of 6 meters per second. So velocity equal 6 meters per second. We know that V is equal to R omega. معناته omega is equal to V divided by R, which is 6 divided by 0.75. The radius that we have, was it 6? It was 0.75, la? The radius that we have found, which is 0.75. So we're going to find out that omega is equal to, omega is 8 radians per second. Okay? Now, if we want to find power, as the question requested, power is going to be torque times omega. So the torque that we have found here, which is 36930 times omega, which is 8 radians per second. Put this into the calculator. So 8 times 36930, 295,440 watts. Remember, the unit of power is watts, or you can simplify it and make it 295.44 kilowatts. All right. And that's pretty much it. This is all you need to know about power. It is equal to the torque times, at least up to this level, it is the torque times the angular velocity. So up to finding the torque, you guys should already know how to do it up till here. Just these extra additional steps is just for finding power. It's just actually one step. You just multiply T by omega. To find omega, you already know how to do this. It is a relation between linear and angular that I have explained before. And then you can find your final power. And that's pretty much it for today.